Assalamu alaikum, sir. I am Muhammad Yasin Arafat. I am from 65B Base Department of Triple E. Here I presentation my Trump paper. Here is the list of context indexed, list of figure, name of the figure, list of equations, name of the equation, list of maths. Mechanical design of overhead lines. An overhead line is subjected to uncertain weather conditions and the external interface. This calls for the use of proper mechanical factors of safely in order to ensure the strength of the line should be such so as to provide against the probable weather conditions. Main components of overhead lines. An overhead lines may be used to transmit or distribute electrical power. The successful operation of the overhead line depends to the great extent upon the mechanical design of the line. While constructing an overhead line, it should be ensured that mechanical strength of the line is such so as to provide against the most probable other conditions. In general, the main components of the overhead lines are conductors. Conductor which generate electrical power from the sending in section to the receiving in section. Supports which may be pole, pulley or tower are keep the constructors at the suitable level above the ground. Insulator. The insulator which are attached to supports and insulated the conductors from the ground. Cross armor. Cross arms which provide support to the insulators. Miscellaneous items such as these floods, dangerous plates, lightning arrestor, anti-clamping wires, etc. Conductor materials. The conductor material used for transmission and distribution of electric power should have the following properties: 1. High electrical conductivity. 2. High tensile strength in order to withstand mechanical stresses. And 3. Low cost so that it can be used for long distance. 4. Low specific gravity so that weight per unit volume is small. All above requirements are not found in a single material. Commonly used conductor materials for overhead lines are copper, aluminum, steel core, aluminum, galvanized steel, and aluminum copper. The choice of a particular material will depend upon the cost, the required electrical and mechanical properties, and the local condition. All conductors used for overhead lines are probably stored there in order to increase the flexibility. In a storage conductor, they are generally on central wire and round this successive layer of containing 6, 12, 18, 24 wires. Thus, if there are an layer, the total number of individual of storing conductor wire is 3 and 1 and plus 1 plus 1. Here in the figure, conductor materials. In the manufacture of standard conductors, the consecutive layers of wires are twisted or spiraled in opposite directions so that layers are bound together. Line support. The supporting structure for overhead line conductor are various types of poles and towers called line supports. In general, the line supports should have the following properties: 1. High mechanical strength to withstand the weight of conductor and wind loads, etc. 2. Light in weight without the loss of mechanical strength. 3. Cheap in cost and economical to maintain. 4. Longer life. 5. Easy assembly of conductors for maintenance. The line supports used for transmission and distribution of electric power are of various types including wooden poles, RCC poles and lattice steel towers. The choice of supporting structure for a particular case depends upon the line span, sectional area, line voltage, cost and local conditions. Wooden pole. Those are made of second wood, solar chair and are suitable for lines of moderate sectional area and of relatively shortly spans, say up to 50 meters. Such supports are cheap, easily available, provide insulating properties and therefore are widely used for distribution purpose in rural area as an economical proposition. Dual double pole structure of an A or S type area. Here tendency to root below the ground level. 2. Comparatively small life 20 by 25 years cannot be used for voltage higher than 20 kV, less mechanical strength and requires proverbial inception. Here is the structure. Wooden poles. Steel poles. The steel poles are often used as the stability for wooden poles. The possess greater mechanical strength, longer life and permit longer spans to be used. Such poles are generally used for distribution purpose in the cities. This type of supports need to be galvanized or pointed in order to prolong life. The steel poles are three types: wise, railed poles, tubular poles, and roller steel joints. RCC poles. The reinforced concrete poles have become very popular as line support in recent years. They have greater mechanical strength, longer life, and permit longer spans than steel poles. The main difficulty with the use of less poles is the high cost of swing out to their heavy weight. Therefore, such poles are often manufactured at the seat in order to avoid heavy cost of transportation. Steel towers. The steel towers are impacted wooden steel towers in steel towers. Here is the steel tower structure. Steel tower structure. Here is the is high 110 kV span 320 meter to 20 kV span 320 meter. Insulator. The overhead lines conductors should be supported on the poles or tower in such a way that current from conductor do not flow to earth. Third, supports, that is, line conductor must be properly insulated from support. In general, insulators should have the following distribution: high mechanical strength in the order to withstand conductor load, wind load, etc. High electrical resistance of insulator material in order to avoid linkage current to a high ratio of puncture strength to falls here. Type of insulator. There are 7 types of insulator, but the most commonly used are pin type, suspension type, string insulator, and second insulator. Pin type insulator. The pin type insulator description. Here is the pin insulator group for conductor shapes or petticoats cementing galvanized steel pin. Pin type insulator. There is a group on the upper end of the insulator. Here is the Safety factor of insulator: puncture strength by flashover voltage. Conductor pin insulator, line conductor, pin type insulator, suspension type insulator. The cost of suspension type insulator is increased as the working voltage increases. Advantage: suspension type insulator are cheaper than pin type insulator for voltage beyond 33 kV. Each unit or dies of suspension type insulator is designed for low voltage, usually 11 kV. The suspension type insulator are generally used with steel tower as the conductor run below the other cross arms of the tower. Therefore, this arrangement provides partial potential from lightning. Strain insulator: when there is a dead end of the line or there is corner or sharp curved line, the line is subjected to greater tension. One low voltage line 11 kV Slackle insulator are used as strain insulator. Here is the structure of strain insulator and stackle insulator. Stackle insulator. In early days, the shoot insulator were used strain insulator. Potential distribution of a suspension insulator strain. Here is the description of potential distribution of a suspension insulator strength. The strength of suspension insulator consists of a number of porcelain discs connected in series of metallic link. The figure of potential distribution: conductor 1, 2, 3 structure. Strain of suspension insulator: the voltage increases on the strain of suspension insulator does not distribution in self insulators does not distribution ties to the basin of shunt capacitors. Strain efficiency: voltage across the strain by N into voltage across dies nearest to conductor. Mathematical expression for potential distribution in suspension 3 dies strain. Here is the figure C1, C2, C3. Applying Kirchhoff's current law to lead A, we get I2 equal I1 plus I1, or V2 WC equal V1 WC into V1 WC1, V2 WC equal V1 WC plus V1 WKC, V2 V1 1 plus K. Applying Kirchhoff's current law to need B, we get 3. Here is the equation from 1, 2 and 3 get Vi by 1, V2 by 1 plus K, V3 by 1 plus 3K plus K square equal V by 1 plus K by K into 3 plus K. Voltage across 2 unit of V1 V by 1 plus K plus 3 by K. Voltage across second unit from V2 equal 1 plus K. Voltage across third unit of V3 equal V1 1 plus 3 K plus K square. Percentage strain efficiency: voltage across range N into voltage across ties nearest to conductor into 100 by V3 into V3 into 100. Methods of improving strain efficiency. Example, here is example. Give me information. Example, strain efficiency. How much strain efficiency? Junction B. Strain efficiency 6.13 kV. Okay. Corona when an alternating potential difference is applied across two conductor whose spacing is large as compared to their diameters. There is no apparent change in the condition of atmospheric air surrounding the wires if the applied voltage is low. Factors affecting the corona: the following are The factor upon which corona depends: atmosphere, conductor size, spacing between conductors, line voltage, critical descriptive voltage. Mm, the potential grading at the conductor surface is given by G equal V by R from E divided by volts by centimeter. The return distance of air at 26 centimeter pressure and temperature of 25 degree centimeter is 30 kV centimeter max. Visual critical voltage VV equal MV0 del R into 1 plus V1 C by del R log E d by R kV phase, where MV is another irregularity factor having a value of 1 part for polished conductors and 0.72 to 0.82 for rock conductor. Power loss due to corona advantage. Corona reduces the effect of transmission produced by surges. Disadvantage: corona is accompanied by the loss of energy. Methods of reducing corona effects: by increasing conductor size, by increasing conductor spacing, sagging over line. The difference in level between points of support and the lowest point on the conductor is called sag. The following points may be noted when the conductor is suspended between two supports at the same level. It takes the shape of century. However, if the sag is very small compared with the span, the sag span curve is like a parabola. The horizontal components of tension is constant throughout the length of the shown in figure 1. When supports are at equal levels, figure where length of span W weight per unit length of conductor T tension in the conductor. Cycle W into L by 2 by whole square by 2 T2 L and omega L square by 80 when supports are at unequal levels. Is the figure. Effect of wind and ice loading. Sag are the true only in still air and the normal temperature when the conductor is acted by its weight only. Total weight of per unit length is Wt equal W plus Wi whole square plus W by W whole square full root over. W weight of conductor per unit length, Wi weight of ice per unit length, W weight force per unit length. Underground cable. An underground cable essentially consists of one or more conductor covered with a suitable insulator and surrounding by a protecting cover. Construction of cable. Cause or conductor, insulator, metallic sheath. Here is a figure. Construction of cables. Bedding, serving. It may not be out of place to mention here that the bedding amount of the serving are only applied to the cables for the potential of conductor, insulator and to the project the metallic sheath for mechanical injury. Classification of cables. The classification, in general, the classification is generally proposed according to which cables can be divided into the following groups: low tension LT cables up to 1000 volt, high tension ST cables up to 11,000 volt, super tension ST cables from 22 kV to 33 kV, extra high tension EST cable from 33 kV to 66 kV, extra super voltage cables beyond 132 kV. Resistance of transmission lines. The effect resistance of the conductor is R equal power loss in conductor by R modulus square. The DC resistance is given by the equation R naught equal rho L by A. The variance of resistance of metallic conductor with temperature is R2 by R1 T plus T2 T plus T1. Example. As example, solution. Schematic courses as a T1 7% increase in resistance. In inductance of conductor due to internal flux. The inductance of transmission line is calculated as flux linkage per ampere. L equal rho by T. The total flux linkage inside the conductor is the figure. A flux linkage between 2 points external to an insulator conductor. Here is the figure and equation. Inductance of a single phase two wire lines is the figure equation. Flux linkage of one conductor in a group. The flux linkage of one conductor in a group of n number of conductor equal into 10 by 7 I1 ln 1 by R prime 1 plus R2 ln 1 by D1 2 I3 ln 1 by D 313 I13 Rn. Inductance of composite conductor lines. Since the single phase line consists of two composite conductors, conduct X, conduct Y, where ds geometric mean ratio and dm geometric mean distance. Here is the example and solution. The GMR for side X. Inductance of three-phase line with equilateral specific is the figure ABC. L equal to into 10 by 7 L1 d by ds is by m. The various inductance per phase is L equal to into 10 by 7 L1 d by q ds is m. In the for the two strand bundle, capacitance of two wire line. Dual lines is the figure and equation. The capacitance of three-phase line with equilateral specific is the figure and equation. Capacitance of three-phase line with unsymmetrical specific is the example. A single circuit three-phase line operates at 60 Hz is the equation solution. Important equation is L equal to into 10 by 7 L dq by ds hm. Here is the equation solution. Q equal reactive power equal Q equal root over 3 VL IL equal 43.5 MVA. Power system stability. The tendency of a power system to develop resistance forces equal to the or greater than the distribution force by maintain the state of equilibrium is known as stability. There is a classification. Steady state stability, transient stability. Steady state stability description, transient stability description. Rotor dynamics and swing equation. Here is the full equation. This is the equation. Power angle equation is mechanical has been represented for transient stability studies by its transient internal voltage in series with transient as shown in figure. The phase angle and the mechanical equantities are measured with respect to the common system reference. In the figure, the bus admittance matrix equation has example single line machine infinite bus system with two parallel lines. As a solution, involving equation P equal P max sin del, where P max equal E prime E1 prime modulus into E prime 2 modulus by x. Here is the solution. Figure the reactance diagram for the single machine infinite bus system. Figure power angle curve equation number 2, example number 2. The single line diagram of figure 1 shows generator comes solution. Figure single machine infinite bus system with two parallel lines. Solution. Admittance diagram and redrawn admittance diagram. Power angle curve solution. Example number 3. The figure the reactance diagram for the single machine infinite bus system. Curve power angle curve equal area criteria. Figure a single machine infinite bus system with plug admits to bus generator is the angle curve critical broken A. Figure power angle curve showing equal period. Initial operating point is A. Critical clearing angle. Figure power angle curve showing critical clearing angle. Critical clearing time TCR equal to root over 4h by dCr minus del 0 Wh by m. Figure power angle curve solution PAR compensation. Is the figure transmission system with both series and shunt compensation. Line length and figure the effect of having only shunt reactor composite on the load reliability. Series compensation. Is the figure effect of having only series compensation on the line reliability. Important expression in BAR compensation. And flexible AC transmission system FACTS. Transmission line can be classified as uncompensated transmission line with series compensation, transmission line with shunt compensation, static synchronous compensation. Here is the ancillation of the operation principle of STATCM. High voltage direct current operate HVDC transmission, monopolar arrangement with ground return, monopolar arrangement with metallic return, on bipolar arrangement, monopolar arrangement with ground return. This is the figure monopolar arrangement with ground return. Monopolar arrangement figure monopolar arrangement with metallic return grounded at one and HVDC transmission line. Bipolar arrangement. Here is the bipolar arrangement figure bipolar arrangement of HVDC transmission system. Here is the generator figure a DC transmission system operating in bipolar mode. Generator, converter, transmission, charger, and converter, DC motor, DC filter, charge, and DC research, CTable, singer instrument, DC filter, DC reactor, DC converter, from the charge and conductor, constituous transfer, shunt operation.